Hi and welcome to video 5, Normal Distributions from Unit 4, Topic 4 of the Math Methods curriculum. And in this video we're going to talk about calculating probabilities on a normal distribution. Yes, that's right, ND is my lazy way of writing normal distribution for actual data, for raw data, for X scores. So, and we call them X scores as I stated there. The real data that can be standardized into Z scores if we need to. And I'm going to show you in this video how on your calculator you might not actually need to. Let's have a quick look at an example. This is the example I'm going to run through, and then we'll do a second example where you can pause and have a go at it first. In a statewide Math B trial, so there was one of these, the data summarized to be X bar is equal to 70 and sigma is equal to 5, which is their percentages. So that means the mean was equal to 70 and the standard deviation was equal to 5. Now, this means that our normal distribution, we're assuming it's normally distributed, will look a bit like this. We have a mean of 70, and then one standard deviation above and below is 65 to 75, and there's 68% of the data in there. And then 60 to 80 contains 95% of the data, so on and so forth. Now, I'm assuming a student can't get above 100%, but we know that a normal distribution goes on to infinity. But that's okay. That's where we get these assumptions running in, going, well, this is our contextual end of domain. Even though the function itself goes to infinity, there's so little data contained in there because 100% is 6 standard deviations above the mean, that it's basically nothing. And 0%, they can't get below 0%, and again, that's basically nothing. So this works, the context works within the theory because there's only a slight variation on what the theory says and what the context needs, and so it's okay. So here's some questions. What is the Z-score of a student with a score of 75, 50, and 72? So recall, of course, that Z is equal to X minus the mean over the standard deviation. And so for the first one, Z of A is equal to 75 minus 70 over 5. And that's, of course, equal to 1. Z of B is equal to 50 minus 70 over 5. And that's equal to negative 4. And Z of C is equal to 72 minus 70 over 5. And that's equal to 0.4. So there are your Z scores for A, B, and C, and the way that we did it. What mark did someone with a Z score of each of these get? So this is now reversing the process to calculate our X scores. X is equal to, this is the rearranged version, Z sigma plus mu. So XA is equal to 2 times 5 plus 70. And so that's equal to 80, and that makes sense because 80 is 2 standard deviations above the mean. 2 is our Z-score, 2 standard deviations is 10 above the mean of 70. XB is equal to negative 3 times 5 plus 70. That, of course, is equal to 55. And XC is equal to 1.7 times 5 plus 70. And that's equal to 78.5. So this is the answer to question 2. And then we've got question 3, which to some extent I may require a calculator for, but I'm actually looking at this and I'm saying, well, this is 1 standard deviation above. I've got that answer in 1A. This is 3 standard deviations below. I've got that answer in 2 part B. And we've got 3 standard deviations below, 1 standard deviation above. So in terms of Z-scores, I will be able to do this quite nicely. But I'm going to also show you how to do it in a calculator using a different technique. But let's start by doing our Z-score conversions. X equals 75 has a Z-score equaling to 1. That's from 1A. And X equals 55 has a Z-score equal to negative 3. And so we have this. Here is our normal distribution. There's our mean, which is 70. Now remember, 50% of our data is on this side and 50% is on this side, which might help us here, because here is our value 75, which is mu plus sigma, just one of them. It's 1 standard deviation above. Now we have, there's negative 1, this is 68% of the data, which means we have 32% of the data on the outside, which means that this is 16% of the data. So the first one, the probability that x is greater than 75, is the probability that z is greater than one standard deviation above the mean, which is 16%, just based purely on our 68, 95, 99.7 rule. 55, on the other hand, is right down here. It's 3 standard deviations below. Right up to there, there is 99.7% of the data, which means that there is 0.15 above and 0.15% below. So that means that the probability for part B is 0.15%, quite low. And then C is the probability that it's in between here. We've already got this bit here is 16%, and this bit is 0.15%, and that leaves 16.15 away from 100, which leaves us 83.85%. Or you might write them as decimals. Now I've got a really important question for you. What kind of magic do cows believe in? Voodoo. If you don't have to pause the video now and laugh for a little while, then you are made of stone. Example 7. Determine that z-score, determine x is between 10 and 12, where x is equivalent to that normal distribution given. Determine A, where the probability of z is less than A equals 0.7. Determine B, where z is between -2 and B equals 0.2. So there's a range of different questions here, and it's actually here that I'll show you how the calculator can be used to help us a bit more. So let's do, first of all, question A. And I'm going to draw a normal distribution for each of these. In fact, what I'm going to do is just go back up here, maybe to here, and I'm just going to steal this image every time. You obviously can't do this in an exam, but I can do it, and I will. Okay, so first we want the probability that z is greater than 0.7. So there's 0.7. I want this probability. Remember, z is greater than 1 from the previous example was 16%. So I'm expecting this to be more than 16%, but nowhere near 50%. So that's what I'm looking at. If I go to my calculator and I'll just exit a couple of times to get back to the main menu, or I'm in the run matrix screen. I go option, statistics, distribution, normal distribution. I want a cumulative, and I want my cumulative to be 0.7 as my lower bound, comma. Now this is where we put in infinity if we want to. You can go and find infinity. It is available here as a symbol in the library, but I would actually suggest you just recognize that 10 standard deviations or above, 100 standard deviations above, that's essentially infinity. So I'm going to do just a high value there for the number, for the z-score. If you're dealing with x scores, be careful that 100 actually is big enough. If the mean was 100, that would be a problem. And then we've got to put in our distribution information. In this case, we've got a standard deviation of 1 and a mean of 0, close brackets, and that gives me 0.2419. So I might just take a screenshot of that and make some quick notes on it for you, just so we've got the syntax right. And so this is, I'll just take this, shoot it there, and the answer to A, the probability that z is greater than or equal to 0.7 is equal to 0.2419 or 0.2420, and we've got our syntax here, and our syntax says that's the lower bound, that's the upper bound, that is sigma, and that is mu. And there's our syntax listed out. So next we have part B, and in part B we need to determine the probability that x is between 10 and 12, where x is approximately equal to the normal distribution 8 and 4. So I'm going to do this in my calculator again, but you'll notice here that this is our normal distribution, this is mu, and this is sigma squared, which means our sigma, our standard deviation, is 2. So this is actually a z-score of 1, and this is a z-score of 2. So we could do this theoretically as well. But let's do it this way. So we're getting our NCD again because it's a cumulative, and our lower value is 10, our upper value is 12, in this case our standard deviation is 2, and our mean is 8, and our answer is 0.136. So I go back here, probably that x is greater than or equal to 10, less than or equal to 12, is equal to 0.136. That's B. And then we have C. Question C, determine A, where the probability that Z is less than A equals 0.7. So again, I'll show you how to do this in your calculator, but let's have a bit of a talk about this as well. A equals 0.7. So if I was to grab a copy of this again, paste that, I want the probability that Z is less than A to be 0.7, so it's going to be up here somewhere. That will be our A. It's going to be above 0 because that has to contain 70% of the data, which means we want the point where that contains 20% of the data. Now, there's not a great deal we can do. There is a nice table that we can use, but it doesn't really exist in your curriculum anymore, so we're going to use our calculator instead. And our calculator has a solve function to do this type of thing. So if I go back to the main menu here and to calculate, I can do solve n, and then I exit that, go back into stats, distribution, normal, NCD. I'm going to do an NCD where the lower bound is negative 100, so I'm just doing something outrageous. The upper bound is A, but I'll just use X. And my distribution is a standard normal distribution, so it's got a standard deviation of 1, a mean of 0, close brackets, equals, so that's shift equals 0.7, and then comma, I want to solve this for x, close brackets, execute, wait, there may be more than one solution, I'll always tell you that, and here's the answer, 0.5244, which is good because A equals 0.5244, it is above the 0 that we expected, and we also know that if we are at 1, this is 16%, which means this is 84%, which is much higher than a 0.7 needed. So we're quite happy with that answer, between 0 and 1. And then we have D. Determine B, where the probability of Z between negative 2 and B is equal to 0.2. And we can do this in the same way. So again, I might actually just go up and use this one, just because it's already there. So just to remind myself, so I want this to be between negative 2 and B is 0.2. So I go back to here. I want that to be negative 2. And I want that to be X. This is still a Z score, still a standard normal. So I've got all this right, but I want this to be equal to 0.2. I'm expecting it to be negative in this case. I'll talk about why in a second. Execute, negative 0.763. So the probability negative 2 is less than Z is less than B equals 0.2 leads to B equals negative 0.763, I think, but I'll just check. Yeah, 763. So there's my solution. Now, if I draw this diagram again, you'll see that negative 2 is here. This is only 2.5%. Remind yourself of the 95 rule. And therefore, this is 47.5% up to the mean. And so I'm expecting a value here somewhere such that this is 20%. And I got a negative. And this may be a little bit closer to 0, to 1. No, a little bit closer to 0 than I expected, but not significantly so. We also have the inverse normal function, and I suggest you look up how to use that as well. That'll work to solve some of these problems also. If you're looking for more information, either ask me as usual or head to page 636 of the Cambridge textbook where they outline how to use some of these functions as well. Either in the run matrix screen, which is great, it's easy to access, you've got your solve n function available, you just need to know the syntax, or you can use the statistics menu, And you don't need to know the syntax. It specifically asks you for specific things, so it makes it a little bit easier to remember. All the best.